Counting is one of the most fundamental things we do. We count the money in our wallets, the number of apples in a fruit bowl, the chocolate bars in a cupboard, and so on. Over time, people have developed many different ways to do this, like scratching lines in stone to count a herd of goats. This helped them keep track of the goats they had, especially if they went missing. Now, of course, this meant that the more objects you had, the more lines you had to draw. And that's not easy when you have hundreds of things to count. Humans needed a much more efficient system than this, something that could handle larger numbers. So, the Romans invented their own numeral system, which used B to represent 5 and X for 10. And like that, more symbols for higher numbers. Similarly, Egyptians also invented their numeral system, who lived around 5000 BC. They even used more creative shapes than just plain old vertical bars, like these circular scribbles for the numbers 10 and 100. This enabled them to write all kinds of numbers, like 324. These days, the most commonly used symbols are 0, 1, 2, and so on, all the way up till 9. It's called the base 10 system. It can represent all numbers, from something as small as 0.0005 to 1 trillion. Can you think of any number that doesn't use these 10 digits? It's impossible. Look at this one. It uses 0, 1, 2, and 4. And even a number as large as this one is still limited to the base 10 system. With base 10, we form the counting or natural set, denoted by a capital N. It goes on forever because natural numbers are infinite. Imagine counting that high. The set of natural numbers can be used to solve many different equations, like this one. Let's try and solve it. Move 1 to the other side and we get x equals 2. In this case, the value of x was a natural number. So, all we needed to represent x was the set n. Would that happen for this equation as well? Let's solve for x to find out. We seem to have run into a problem. X equals 0, but we don't have 0 in the natural set. What do? Simple, just add it in. This makes an entirely new set called the whole numbers. We represent it with capital W. Problem solved. Now, let's see if this works for another equation. Let's solve the equation by isolating x on one side. And immediately you get x equals minus 2, a negative number. But all our whole numbers are positive. Luckily, every natural number like 1, 2, 3 and 4 has a negative counterpart, minus 1, minus 2, minus 3 or minus 4. This gives us a new set of numbers called integers, which contains both whole numbers and negative numbers. The positive integers sit on the right side of 0, while the negative integers are on its left side. We also denote this set with an alphabet, the letter Z, which we can also write in this way. Of course, you don't need negative numbers to count those chocolate bars or your money. It would be sad to have negative 1000 rupees. But integers are useful in solving any equation where the larger number is subtracted from the smaller number, like the equation we just saw. These sets of numbers don't end there, however, and it's not like we enjoy making things more complicated for you. But we have plenty more equations to solve, which require plenty more kinds of numbers. Therefore, in the next lesson, we'll look at rational and irrational numbers and we promise you'll find them very helpful.